Namaskar. So let's start the next version of the tutorial. We are into FPGA design based on Xilinx AMD Spartan 7 series. So we were there with like FPGA overview. Before proceeding to this document, let me highlight the agendas that we will be discussing in this. First of all, I would like to tell you that the audiences will be for this particular tutorial is students who are looking for core FPGA design concepts and want to make their career in FPGA based designs, and the professionals who are trying to develop some hardware based on FPGAs. This particular device which I am going to explain, the same concept can be extended to any other device based on 7 series, not only a Spartan 7, it can be other series as well like RTX, Kintex and VTX. Okay, but our main focus is Spartan 7 XC7S50 series. All right. The contents that we will be doing in this tutorial is like what is the selection process and details of a Spartan 7, then hardware design architecture and the flow, like what are the blocks that we will be putting before starting our hardware design. Let's say basically we have our FPGA. So what are the different blocks that we should like put before like proceeding to design? All right. So it can be like power, then it can be like configuration, or it can be let's say EEPROM interface. Okay, it can be like our user IO, whether it is push buttons or LEDs or anything, right? Then it can be like SPI interface, then it can be your UART, USB bridge. It can be even like flash memory interface. And the very good thing that we will be discussing in our complete board design is our DDR3 interfacing. All right. So all these things, then power sequencing up and down, all these things we'll see. Then we will be having configurations like based on JTAG or SPI or quad SPI. Then configuration modes, I will be basically explaining you master, slave and JTAG boundary scan. More configuration modes are also available, but we will be concentrating on these three options. What are the different clocks, how you can generate a different clocks to like enable the FPGA. Then decoupling capacitor selections, like suppose all those your power pins are there like VCC, INT, auxiliary and like block RAM, ADC, all those power rails are there, right? So what are the decoupling capacitors that you should be giving to them? Then GPIOs and their design considerations, where they should be left out or all these things. And as I mentioned already, the different interfaces of memory devices and all those things. At last, we will see PCB design guidelines. So these are the things we will be covering. So let's proceed. In datasheet overview, we have seen a Spartan 7 already we have selected the device that was selected based on Spartan 7, and we have enough number of logic cells and all these things, so we no need to worry about. Then you can see based on the like family, we have logic cells, number of logic cells like 6,000, 12,000, 23,000 and 52,000 around. Okay, so our main focus is XC7S50. Okay, as you can see, this device was selected because it has a compatibility to 4 devices uh, from XC7S6 to 15, 25 and 50. So if you want to reduce your development cost or your FPGA cost, once you have designed with XC7S50, you can directly replace that device with 25, 15 or 6. There is no need to change any much. All right, and this is a optimum number of IOs is also available, so uh, we can easily, do these things. Our main, application design will be basically some user interface where you are going to control some like push buttons or some LEDs, or you are going to have some memory device interfaces like EEPROM, even DDR. At last I'll tell you like how to interface this, but basically I'll recommend for DDR interface you have to have a little bit higher number of like pins. For example, you can go ahead with 250 IOs or 484 pin configurations. This is much more better or much suggested. All right. In this overview document, more things are there, like it is having RTX 7 and other series as well, but we don't have to go ahead with this. So I am skipping RTX and Kintex and VTEX. Rest, what are the things that is given in this overview is basically stacked silicon interconnect technology. So basically, all those terminologies that you will be seeing in separate documents, well, like explained manner, those all are there here in a summary manner. Okay, so this configuration logic blocks or lookup tables, slices, all these things are there. Then clock management is there. So this you don't have to go ahead right now here, because this will be discussed in each and every uh, related documents. Okay, so I'll just go down directly. IO characteristics, then transmitter, receivers, configurations, then yes, it has even analog to digital converters. But basically I'll suggest for high-end application, try to use separate ADCs. Okay, don't try to use the inbuilt FPGA ADCs, but for very small application you can utilize the ADC itself. That is not a problem at all. But I'll recommend you to use a separate ADCs. There are a lot of ADCs available from analog devices or linear technologies and all, even Texas Instruments. Okay, good. So next thing is ordering information. I'll tell you again because this is most important thing before selecting your device. So I'll go ahead with Spartan 7, and you can see all the devices are having either commercial, extended or industrial. So I have availability only commercial and industrial. In commercial you have 2 and 1, both the speed grades are available. 2 is mid range and 1 is slow grade. Okay, so I have selected 2. You have industrial grade as well. Like industrial is basically like little bit higher temperature up to 100 degrees centigrade, whereas commercial is up to 85 degrees centigrade only. Okay, if you want to go ahead with a little much higher temperature range, then you can go ahead with 1Q. So that is availability. Now the most important thing is ordering this. So if you go ahead with a Spartan 7, what you can see, XC7. So XC7 is our device. So you can see XC7. Then S is for a Spartan, K will be for like Kintex, or A will be for RTX, and then 50. So this is our device type. Then speed grade, I'm going to take the little bit mid range, so that is -2. Then here we have FG or FB or FT. So all these informations were there in the device type above. So you can go there and then find out which one to select. So I remember, so I will put it FT. Then G is for ROHS. Since I am going to work with 196 pins, so I will take it up as B196, and then I am going to work with commercial grade, so we will be taking C. So this is our complete part number of the device, and in short I will be discussing only this much. Okay, so So only this much will be always taken into account. Now you can same way order the device based on Kintex or other devices as well. So let us now proceed the very important task, which will be our power supply sequence. Next one. Okay. So for going to power schemes, we will open a document which is called ACDC characteristics. Okay, ACDC characteristics. So you can find all these documents in here itself. Like you have product selection guidelines, and you can directly open. Arctic 7 is actually containing a Spartan 7 as well. So you can open this DS181. Okay. So DS181 DC AC switching characteristics. If you open this, you will find out this document. So in this particular document, what we'll try to find out is what are the different powers that is required for our FPGA. So let us first talk about absolute maximum rating. Whenever you read a data sheet, I'll recommend you proceed in this manner. First is what is the absolute maximum rating. So these things is there in your mind. Like you will not allow any voltage going into VCC INT pin more than 1.1 volt. Okay. So 1.1 volt is maximum. Similarly, auxiliary voltage is 2 volt and block RAM voltage is 1.1 volt, and VCCO, that is IO voltage, is 3.6 volt maximum, and reference is 2 volt, and all these things similarly, right? So since we have limited ourselves what is the maximum voltage that will be applied, now we will proceed to operating voltage. Okay, it is still absolute maximum rating, so you don't have to worry about maximum ratings. Now we'll talk about recommended operating. So this is the thing that you should immediately open some PPT or Word document and note these values, so that while designing it will be helpful to you. Okay, so our core voltage is like internal supply voltage is, I'll take up 1 volt. Okay, because this is our design. So our design is based on speed 2 or 1, both are same design, so it will be 1 volt. Then the auxiliary voltage, I will be generating a voltage of 1.8 volt. Then block RAM voltage similar to internal supply voltage, that is 1 volt. Then our VCCO, this can go up to 3.456 volt, but still what I'll recommend is we will be using 3.3 volt IOs or 2.5 volt IOs. So two labels I will be using. Okay, so we'll be going with 3.3 volt. All the IOs will be enabled with this, like logic labels will be 3.3 volt or 0. You can see we have ADC voltage. So ADC, if you want to utilize ADC, then you have internal ADC available 1.8. Okay, VCC ADC you can supply 1.8 volt, or externally if you want to give a reference, then you can put it 1.25 volt. Okay, and since we have selected this temperature, which is commercial, which is going to 0 to 85 degrees centigrade. So these are the most important like a parameter that you should look into before even thinking of your power supply scheme. Okay, so these are the things that we need. So what is the thing that we need? We need VCC INT 1 volt, VRAM, VCC auxiliary, VCCO, and ADC and V reference. Okay, so these are the voltages that I will be generating or I will be trying to generate. Okay, next is our DC characteristic over recommended operating conditions. So there are a lot of other things are there which is unnecessary. However, you can see some of the notes that is there here, like a total of 200 milliampere per bank should not be exceeded. Like maximum consumption will be 200 milliampere. So you will come to know like what is the like current that will be required for designing your power supply. Okay, good. Proceeding to next thing, like overshoot undershoot, that I will be not talking about because we have already talked about the operating voltage, and there the accuracy was given, so we'll try to achieve that. Next is typical quiescent supply current is also given. So if you want to read it, you can read it. Otherwise, there is no need at all. Okay. Next is very good. So once we proceed to power on off sequencing, like see, once we select a regulator, whether it is a linear regulator or it is a switching regulator or it is our PMIC, like power management IC. So basically I'll recommend you, if you have very high-end application, but you can, give a little bit time in testing, you go ahead with PMICs, okay, unless it is required your linear regulator, okay. So if you have a very tight recommend, like a requirement of noise or something, then you can go ahead with linear regulator. Otherwise PMIC is much easier to proceed. So the power on sequencing is, first of all, you should have VCC INT, then VCC block RAM, auxiliary, then VCCO. This is the sequence that you should maintain. Even if you do not maintain, the FPGA will work, but there may be little bit of problem, like while switching off or switching on. So recommend you to, like follow the process of power on sequencing. And then recommended power of sequencing is reverse order of this. Okay, so the reverse order will be VCCO will be switched off first, then this, and then this, and then this. So if I put it in a diagram, I can tell, let's say I am going to enable my regulator. So once you have enabled it, this will be the first one, which will be VCC INT, which is enabled after some delay that you want to give. Okay, then I will enable VCC VRAM, so that is number 2. Then number 3 will be sorry, number 3 will be auxiliary and VCCO. So number 3 will be auxiliary, that is this, and then number 4 will be VCCO. And while switching off, you can see I have switched off my VCCO first. Okay, so I have switched off, then after some delay I will be switching off my third one, which is auxiliary, then second one, which is BRAM, and then first one, which is internal supply voltage. So internal supply voltage was switched on first and switched off last. Okay, so first on and last off. So this is the way we will be proceeding. Actually, if I tell you a like a ready-made solution, it is kind of like this, that we have enabled, and enable channel 1 will be enabled after some time, then channel 2, channel 3, channel 4, and similarly there will be off sequences, which will be first this, then this, then this, then this. Okay, next, proceeding to next one, our power on sequence for RTX devices and all those things are given, but it is not like needed right now. Next, the very important thing that we have to take care of after power on of sequence is the ramp up time. Like any power that you are going to, like switch on, it should be very immediate or it should be having some delay. Okay, so this is called ramp up time. Okay, so this ramp up time, you can see the VCC INT minimum is 0.2 and maximum is 50 milliseconds. So I will try to keep around, like let's say 2 millisecond, or let's say some 2 to 5 millisecond. That will be my recommendation to keep. Okay, so for VCC INT, ramp up time will be 2 millisecond to 5 millisecond in our design. Similarly, we will try to keep each power ramp up time, uh, between 2 to 5 milliseconds, so that it meets between minimum to maximum requirement. So this is the one more important table that you should keep in your design document. Okay, now this you don't have to, take care of, like this is in DC input and output levels. So if you are working with high speed terminal levels, then you can go ahead with minimum, maximum. So this you can read it, but there is no need, like whatever voltage you have given, that only it will be taken care. Okay, coming to the next one, we will go ahead quickly the other parts of the document. We have switching characteristics, other things. So it has around 64 pages of documents, and the amount of informations that I have given you is more than enough for your power supply sequencing and power supply design considerations. Okay, coming to the performance characteristics and these things, this you don't have to worry about. Then in our upcoming sessions, we will talk about other devices as well. However, this delay measurement techniques and all these things are given. So for very deep level designing, you will have to read all these things by yourself. But in my tutorial, I will be giving you what is required. Okay. So let me quickly move down. So coming down, you can see PLL application specification and everything is given, like what should be our speed grade and what should be the maximum and minimum like I mean speeds. So you can see PLL input maximum is 800 megahertz and input minimum is 19 megahertz. So your aim should be to keep your PLL frequency in between these two frequencies. So let's say we will be working around, let's say 100 megahertz. Okay, so like that we will be working, or 200 megahertz. Similar to that, you have clock capabilities, like what is the delay time between clocks. So hope you have a good understanding now, like what is the DCAC characteristics and how you will be taking care of your uh, power supply design, right? Now, if you do have any question regarding power supply design, then you put your comments in your in the comments below. Otherwise, I will be moving to finding a power supply. Regulators, whether it will be a PMIC or linear regulator or buck regulators or boost regulators. Based on that, I will be trying to like give you a solution. Okay, but before that, we will have just quick review of available ADC. So the ADC specification, as you can see, that it has VCC ADC as 1.8 volt plus minus 5%. The reference is internal reference, which was 1.25 volt, and which is positive, and negative is 0. Okay, which is grounded. The clock is 26 megahertz that they are using. If you want, you can use a little bit more as well. Okay, anyway, based on these specifications, our ADC resolution is 12 bits. Then we have very good linearity and integral non-linearity and differential non-linearity. So these two it can be used. So if you are using your ADC from FPGA, you have to take care of this, like it has 12-bit resolution. Okay, and it has good gain error and everything. So this is very good to utilize. So in my application circuit, in my application design, I have introduced two channels of ADC as well, so that your design will be very flexible, like you can utilize the FPGA internal ADC as well. Okay, now moving to this configuration switching characteristics. So I'll talk about more in like configuration methods. So switching characteristics and all these things that will be taken care by programmer, who will try to keep the program latency maximum it should be this much millisecond, that is 5 millisecond. So he should not exceed program latency more than 5 millisecond, or power on reset time. Based on this, what should be the minimum maximum values of uh, power on reset and programming time, right? So all these things, this will be taken care during the program. And you can see the clock output master modes, what is the clock output timing and delay, and what is the frequency. Master frequency is 100 megahertz maximum or 70 megahertz. Similarly, in slave mode, what should be the slave frequency? That will be again same. So see, these are 100 megahertz, 100 megahertz. You can see the device that you have selected first, like what is the speed grade 1, and this is slowest. So slowest one you see, okay, 1 volt, this one. So this column or this column, if you have selected 2, then this column you see. So in this column you can see you have 100 megahertz maximum, you have 100 megahertz maximum. So our aim is to work with around 40 megahertz. So we will be designing our uh, clock generators and all those things based on 40 megahertz working or something like that. All right. Good. So this is what the AC/DC switching characteristics documents explanation was, and you can see you have come to the end of power supply sequencing and power supply requirements and all these things. So put down your comments or your questions that is there in terms of power supply identification, like what are the voltages that is required for your FPGA. Okay. In next tutorial, we'll try to move ahead with finding a regulator, and we'll design our all these voltage rails based on the required voltage and current ratings. Thank you so much. Bye.